Okay, so what I want you guys to do in this lesson, this is a continuation still of 1.6, but we're going to look at applying the law of sines to some different types of problems. So what I want you to focus on here is not so much the law of sines piece, but how can we set up and draw our diagrams, because the diagram piece is the most important piece to solving any of these application problems. Okay, so commonly you'll see lots of bearings in laws of sines problems. And a bearing is something that indicates the direction that something is traveling. Okay, so sometimes it's not a moving object. Sometimes a bearing will indicate where one object is in relationship to another object. So that's another kind of way that you might use bearings. So I'll try to give examples of both here. But let's talk about what a bearing is. Since it tells us a direction, we want to think about the bearing in relationship to a compass, okay? So let's say we have a boat that sails on a bearing of north 43 degrees east. So let's break down what north 43 degrees east means. The first direction here tells you where you start on your compass. So you're going to start facing north. The degree tells you how far you're going to rotate. And then the last letter that's written there is indicating which direction you rotate. So if I'm looking at a bearing of north 43 degrees east, we're going to think about something that is facing north, and then we're going to rotate that 43 degrees towards east. So in this case, that's going to be in a clockwise rotation. Okay. Now what I would do is I'd go ahead and I would label this angle right here is 43 degrees. And I do something like this where I'd put that in there and then maybe even put in a little arc so we knew for sure that's the angle we're talking about. So this is a great diagram that shows us our boat traveling at a bearing of north 43 degrees east. Okay, so let's look at one other example of some bearings, and then we'll talk about an actual problem that you have to set up. So let's just say we have a plane flying on a bearing of west 112 degrees south. Okay, normally, well, not normally, usually the angle that's given to you here is an angle that is acute. Usually bearings give us values that are between 0 and 90, but not always. So I wanted to give you an example of how that might happen. So our plane is flying west 112 degrees south. So we're going to start with an arrow facing in the west direction. And since I'm going towards south, I'm going to rotate in the clockwise direction again. So this time we're going to rotate from facing west, we're going to rotate 112 degrees. So that would be about right here. Now in this case, I know that we have an angle that's 112 degrees, but that happens to be this whole big angle here. So you might want to consider the fact that 112 minus 90 is 22, so you actually have that angle as well. You would know that this little guy in here was 22 degrees. So that might be information that you need to solve the problem, to set up your triangle in a way that you can use the law of sines. Maybe not, it just kind of depends on the problem, but it's always good to label as much information as you possibly can. Now, before we actually walk through one of these problems, another property that you end up using a lot in these types of problems takes you back to something that I hope you learned in geometry, and it has to do with parallel lines. So in many problems that involve these bearings, or sometimes even angles of elevation and angles of depression, you need to look at the properties of parallel lines. And there's two that come up the most often. The first one is that alternate interior angles are congruent. So if you have two parallel lines, you know for a fact the alternate interior angles are congruent. So those angles are like here and here. They're on alternating sides of this line here, which we call a transversal, and they're inside the parallel lines. So for example, these two angles that I've highlighted in yellow would be congruent or the same size, or these two angles that I'm highlighting in blue right now would be exactly the same size as well. those are probably the ones that you are going to use the most often. And it's important because as you're labeling your diagram, if I know this angle right here, now I also know this angle right here, and this might be the angle that I'm actually interested in to set up the law of sines and solve for whatever piece that I'm looking for. The other angles that are congruent are corresponding angles. So corresponding angles are on the same side of this line that we call the transversal, but one is inside the parallel lines and one is outside. So for example, where I have these two blue dots, those are corresponding angles. And you can see they're both obtuse. They look like they're the same size. They are the same size. So those would be congruent. Or these two yellow angles are now corresponding angles, so they would be congruent. Or you could look at the other side of the transversal. Those angles would be congruent as well. So I just wanted to remind you of this property because it pops up a lot. Okay, so now let's look at an example. And I'm not going to focus on the math piece of this, like setting up the equations and solving everything. I'm going to focus on setting up and drawing the diagram. So in this example, we're looking at a boat race, and the course for a boat race starts at point A and proceeds in the direction of south 52 degrees west, and then it goes to point B. Then it changes direction. It goes south 40 degrees east to point C, and then finally the boats all turn and go back to point A. We know that point C lies 8 kilometers directly south of point A. Your job is to approximate the total distance of the race course. Now we know we have 3 points, A, B, and C, so we know we're going to have a triangle. Great. Now we got to figure out what this is going to look like. All right, so let's say we got point A here, and I'll just put it, I don't know, maybe right about there, right? Now, before I even worry about point B, I'm just going to give myself an idea of where point C is. I know that point C is directly south of point A, so I'm just going to put it right there for now, and I'll move it if I need to, but it's going to be somewhere around there, and I'm just keeping that in mind because it's helpful when we're putting all this together. Now, one of the things that I always want you to do when you're working with a bearing problem, I want you to draw the little crosshairs of the compass every single time you're trying to figure out a bearing. Okay, so we know that the race starts at point A and it proceeds in the direction of south 52 degrees west. So let's draw a little arrow for us facing in the south direction. Don't you guys draw that arrow, but think about it with me for a second. Now, from point A to point B, we're going in the direction of south 52 degrees west. So from the south, I'm going to rotate 52 degrees towards west. So that happens to be in the counterclockwise direction. So that's about right here. So I'm going to put point B right there. Okay. And I'm going to label my 52 degrees. And this is why you need those little crosshairs, because this little angle that I've just made only exists if you have a reference of where south is as well. So this little angle right here is 52 degrees. All right, so now the boats are going to turn and they're going to go south 40 degrees east from point B to point C. So again, I need those little crosshairs. So we're going to draw them at point B, give ourselves a little arrow, and this time we're starting from the south direction, but we're going to rotate towards east. So east is over here, and we're going to rotate 40 degrees towards east. I'm going to make it quite long because I know that C happens to be directly south of point A. All right, so here's again why I needed those little crosshairs. This little angle right in there is my 40-degree angle. I'll make it a little smaller so we can fit it in there. Okay, now we need one more segment so we can finish the triangle here. And that's going to go from A to C like this. So let's take C and put it right down here where it's supposed to be. Oops. Come on, C, let's go. There we go. All right, so there's point C. And you know what I'm going to do? I'm going to take those crosshairs and I'm going to put another one at C as well, even though I'm not looking at a bearing from C, but it's going to help me fill in some additional information that I need. Remember, we also knew that point C lies 8 kilometers directly south of point A, so I'll put my 8 kilometers in right there. Okay. So we have one side, we have one angle inside the triangle, we have one angle outside the triangle. In order to use the law of sines, we definitely have to have a little bit more information than this. If I want to approximate the total distance of the race course, basically what I want to find is side A over here and then side C over here, because I already know side B across from angle B, it's 8 kilometers. So if I had all those three sides, I could just add them all up and then I could get the total distance of the race course, right? Okay, so remember how I told you parallel lines are going to come into play frequently? Well, they do right here. So this line, this north-south line, is running parallel to that north-south line, and here is a transversal going between them, right? Now I knew that this angle right here was 40 degrees. That means that I know this angle right here is 40 degrees. Those are alternate interior angles, and that's really good news because that means, I'm not sure, yeah, that's what I'm afraid of. That means that I've got a second angle of my triangle here, which I absolutely need. So we'll take that 40 degrees, and now we know this is 40 right here, right? Okay, so there's my parallel lines, there's my transversal, and there's my alternate interior angles, right? Okay, so now that I know this angle is 52, this angle is 40, I can add those together and subtract from 180, and then that'll give me the last angle of the triangle is, I believe, 88 degrees once I add those together and subtract from 180. Now 88 is this whole big angle, and I've got crosshairs in there, so it'd probably be a good idea to show that 88 is that whole big angle. Okay? All right, so there's setting up my diagram. That's everything that I need. You might want to, take away some of these highlighting things and make the, picture a little less crowded, I guess. So I'll take away all those things in there. So I got my triangle. I got one side. Now you could set up the law of sines, and you could say that side A over the sine of 52 would be equal to side B 8 over the sine of 88, and that would be equal to side C over the sine of 40. And then, of course, you just take one ratio or one proportion at a time. So first I might solve for side A, then I might solve for side C, then I'd add them all up, and then I'd have the total distance of the race course. Okay, so there's a few examples that have to do with bearings and parallel lines. The application problems really are all about reading and drawing the picture correctly. So we'll work on that in class on Monday or Tuesday.